Imagine you wake up tomorrow to breaking news. A radio telescope has picked up a clear, intelligent signal from another civilization. It is not random noise, not a pulsar, but a deliberate message. Your first reaction would likely be excitement. Finally, proof that we are not alone. But then a deeper question emerges, one that physicists and astronomers quietly wrestle with. If intelligent life is common, why has the universe remained so silent for so long? Why, in a cosmos filled with hundreds of billions of galaxies, each containing hundreds of billions of stars, do we see no obvious signs of engineering on cosmic scales? You might assume that intelligence is a natural outcome of evolution. Give a planet enough time and clever creatures will eventually appear. But physics has a way of crushing what feels inevitable. The universe, when you look closely, seems incredibly good at making simple things, atoms, stars, dust, but remarkably bad at sustaining the fragile chain of events that leads to technology, consciousness, and radio transmitters. Tonight, I want to take you on a journey, not to argue that intelligent life is impossible, but to show why, from the viewpoint of physics, chemistry, and cosmic history, it may be astonishingly rare. And the surprise is this: the rarity may not come from one dramatic barrier, but from a long series of unlikely physical circumstances stacked like a tower of balanced coins. Let's begin somewhere very ordinary. You are sitting in a room breathing air warmed by sunlight that left the sun 8 minutes ago. You drink water made from hydrogen forged in the Big Bang and oxygen produced inside exploding stars. Everything around you feels stable and predictable. Gravity holds you to the ground. Molecules hold your body together. The Earth spins without throwing you into space. This everyday stability gives us a false sense that the universe is welcoming. We assume planets are plentiful, climates are gentle, and chemistry easily organizes into life. But physics tells a harsher story. Most of the universe is empty vacuum. Most stars are hostile furnaces blasting radiation. Most planets are frozen, scorched, or violently unstable. Imagine throwing darts randomly at a map of the cosmos. The odds of landing on a calm, rocky planet with liquid water, a protective atmosphere, and long-term stability are already surprisingly small, but even that is just the beginning. Life requires not only the right temperature and chemistry, but also time. Billions of years without catastrophic disruption. One nearby supernova at the wrong moment could sterilize an entire biosphere. A chaotic orbital shift could freeze oceans or boil them away. When we say Earth feels normal, we are committing a subtle logical error. We observe conditions compatible with our existence precisely because we exist here to observe them. Physics calls this an observational bias, and it quietly hides how extraordinary our environment may be. Let's rewind the cosmic clock and ask a more basic question. How did the ingredients for life appear at all? After the Big Bang, the universe contained mostly hydrogen and helium. No carbon, no oxygen, no nitrogen, none of the complex elements required for biology. Those elements were forged inside massive stars through nuclear fusion and then scattered by supernova explosions. That means life depends on at least one earlier generation of stars living and dying. But massive stars are short-lived and violent. They flood nearby space with radiation and shock waves. So for life to arise, you need just the right distance from stellar chaos. Not too close to be sterilized, not too far to lack heavy elements. It is a cosmic Goldilocks zone, not only around a star, but within a galaxy. Too near the galactic center, and supernovae become frequent. Too far in the outskirts, and heavy elements become scarce. Our sun sits in a relatively calm region, orbiting between spiral arms, like a traveler staying between busy highways. That stability has lasted for billions of years, allowing life to evolve slowly. But think about what that implies. Intelligent life may require not just a habitable planet, but a habitable galactic neighborhood, a constraint imposed not by biology, but by astrophysical dynamics. Historically, our understanding of these conditions evolved through scientific surprises. Galileo first revealed that Earth is not the center of the cosmos. Newton showed that the same gravitational laws govern falling apples and orbiting planets, unifying heaven and Earth into one physical system. Later, astronomers discovered that stars are distant suns, each potentially hosting planets. For a while, optimism soared. Maybe life is everywhere. But then came the 20th century, and physics started adding complications. Stellar evolution revealed that many stars are unstable or emit violent flares. Planetary science showed that most planets we observe are gas giants or tidally locked worlds with extreme environments. The more we learned, the more we realized Earth is not merely average. Consider our moon. It stabilizes Earth's axial tilt, moderating climate over millions of years. Without that stabilization, chaotic shifts in tilt could produce extreme climatic swings that disrupt complex ecosystems. The Moon likely formed from a rare giant impact early in Earth's history, a chaotic collision that could easily have destroyed the planet instead, yet somehow it produced a stable companion that may have played a role in making Earth's environment long-term habitable. Physics does not say this is impossible elsewhere, but it reminds us that planetary histories are violent and unpredictable. Now let's approach a deeper conceptual breakthrough. Life at its core is a battle against entropy. The second law of thermodynamics tells us that disorder tends to increase. Left alone, complex structures decay, stars burn out, molecules break apart. Intelligent organisms require constant energy flow to maintain order. Sunlight driving chemical reactions, metabolism maintaining structure, but stable energy flows are delicate. Too little energy and chemistry freezes. Too much and complex molecules are destroyed. Earth receives just enough solar energy to maintain liquid water without sterilizing radiation. But even that balance has shifted over time. The sun was dimmer billions of years ago, yet Earth avoided freezing thanks to atmospheric feedbacks like greenhouse gases. That delicate interplay between astrophysics and atmospheric chemistry may be rare. When we consider intelligent life, the challenge becomes even greater. Evolution must climb a long ladder of complexity, from simple self-replicating molecules to cells, multicellular organisms, nervous systems, and eventually technological intelligence. Each step is not guaranteed by physics. Natural selection works with whatever random mutations appear, and catastrophic events, asteroid impacts, volcanic winters, mass extinctions, reset progress unpredictably. Physics sets the stage, but contingency writes much of the script. Let's perform a thought experiment. Imagine you are given a box filled with billions of tiny components, atoms, molecules, dust, and you shake it randomly. Will it assemble a functioning computer? Of course not. Complex systems require specific sequences of interactions over time. Evolution is not random shaking. It is guided by selection pressures. But the initial emergence of life may require rare chemical pathways. We still do not fully understand how non-living chemistry transitioned into self-replicating systems. Experiments show that organic molecules form naturally in certain environments such as hydrothermal vents or early planetary atmospheres. But bridging the gap between simple chemistry and robust cellular life remains an unsolved problem. Physics can describe the energy landscapes and reaction rates, but it does not guarantee that a stable self-replicating system emerges frequently. If that step is extremely rare, then intelligent life becomes rare almost automatically. Even if microbial life is common, the path toward complex intelligence may involve additional improbable transitions. On Earth, for example, multicellular life appeared relatively late in history, and technological intelligence only emerged in the last tiny fraction of geological time. Another physical constraint involves planetary stability over billions of years. Plate tectonics, driven by internal heat from radioactive decay and residual formation energy, plays a crucial role in regulating Earth's climate by recycling carbon between the atmosphere and the crust. Without that geological thermostat, Earth might have become a frozen snowball or a runaway greenhouse like Venus. But plate tectonics requires a specific balance of planetary mass, internal composition, and thermal history. Too small a planet cools quickly and becomes geologically dead. Too large, and pressures may create exotic interior states that behave differently. Magnetic fields also matter. Earth's magnetic field shields the atmosphere from solar wind, preventing erosion of water and air. Mars, lacking a strong magnetic field, lost much of its atmosphere early in its history. Again, physics does not forbid these favorable conditions elsewhere, but each requirement narrows the range of possible habitable worlds. As we move deeper into modern science, we encounter a puzzling observation known informally as the cosmic silence problem. Given the vast age and size of the universe, even a small fraction of planets developing technological civilizations could fill galaxies with detectable signals or megastructures over millions of years, a blink of an eye on cosmic timescales. Yet, our telescopes see no unambiguous evidence. Is this because intelligent life is rare, or because technological civilizations are short-lived? Physics offers several sobering possibilities. Advanced technologies may carry risks. Nuclear weapons, engineered pathogens, runaway artificial systems could limit longevity. But even without speculation about behavior, there are physical barriers to interstellar expansion. Space is unimaginably vast. The nearest star is over 4 light-years away. At realistic propulsion speeds, travel between stars takes decades or centuries. Radiation exposure, resource constraints, and the energy cost of accelerating massive spacecraft present formidable challenges. Colonizing a galaxy may be far more difficult than science fiction suggests. Perhaps intelligent species remain isolated like distant islands in a cosmic ocean, each separated by enormous gulfs of space and time. Let's return to a more intimate scale and ask what intelligence actually requires from a physical standpoint. Brains are energy-hungry organs. Human brains consume roughly 20% of our resting metabolic energy. That energy must come from a stable food web supported by photosynthesis or chemosynthesis. Evolutionary pathways leading to large brains depend on environmental pressures favoring complex behavior, social structures, and long developmental periods. Those pressures are contingent on ecological history. For billions of years, Earth was dominated by single-celled organisms. Even after multicellular life emerged, intelligence was not inevitable. Dinosaurs ruled the planet for over 150 million years without developing radio telescopes. Intelligence may be a rare evolutionary strategy rather than a predictable outcome. Physics cannot dictate evolutionary goals, but it constrains the environments in which complex nervous systems can evolve. Stable climates, sufficient oxygen levels, and long-term ecological niches that reward learning and cooperation. Here's another thought experiment. Imagine rewinding Earth's history to the time before complex animals existed and letting evolution run again. Would intelligent humans appear? Many biologists suspect the answer is no. Evolution is path-dependent. Small changes early on could lead to entirely different outcomes. From a physical perspective, this sensitivity resembles chaotic systems where tiny variations in initial conditions produce vastly different results over time. The emergence of intelligence may be less like a clock ticking toward a predetermined event and more like a branching tree where only a few branches lead to technological civilization. When you combine astrophysical rarity, chemical uncertainty, evolutionary contingency, and technological fragility, you begin to see why the universe might be largely silent, even if life exists elsewhere. But we must be intellectually honest. Our sample size is 1. We know life arose on Earth relatively quickly after conditions stabilized, which could suggest that simple life is common. We also know that complex intelligence appeared only once, at least in technological form, which could suggest rarity, but we cannot yet draw firm statistical conclusions. Astronomy is rapidly discovering exoplanets, some Earth-sized and within habitable zones. Future telescopes may detect biosignatures, gases like oxygen or methane in planetary atmospheres that hint at life. Physics provides the tools to analyze these signals through spectroscopy and atmospheric modeling. We stand at the threshold of a new era where the question of life's prevalence may shift from philosophy to observation. And if we find microbial life everywhere, but intelligence signals nowhere, that would support the idea that intelligence is an unusual evolutionary leap rather than a common endpoint. Let's explore another counterintuitive implication of physics. Time itself may limit the spread of intelligence. The universe has a finite age, about 13.8 billion years. Heavy elements needed for life accumulated gradually. Early galaxies lacked the chemical richness required for rocky planets. Meanwhile, stars have finite lifetimes. Red dwarf stars can live trillions of years, far longer than our sun, but many emit powerful flares that may strip atmospheres from nearby planets. Perhaps we are early in cosmic history relative to the potential lifespan of habitable worlds. Intelligent life may be rare now simply because the universe has not yet matured enough. Alternatively, it may be that intelligent civilizations tend to arise but also fade quickly on geological timescales, leaving only faint transient traces. Physics does not tell us which scenario is correct, but it reminds us that cosmic history is dynamic and evolving. Consider communication itself. Radio waves travel at the speed of light, which is fast but finite. If two civilizations are separated by thousands of light years, a single conversation could take millennia. Signals weaken with distance, dispersing into cosmic noise. Detecting them requires enormous antennas and careful analysis. We may be listening during a brief technological window when civilizations use detectable signals before transitioning to more efficient or private communication methods. So the silence may reflect not absence, but misalignment in time and technology. Again, physics sets the constraints: signal attenuation, cosmic background noise, and the inverse square law governing radiation intensity. Let's pause and reflect philosophically. Humans often imagine intelligence as the pinnacle of evolution because we are intelligent, but physics is indifferent to our aspirations. The universe is vast, cold, and mostly lifeless, yet capable of producing extraordinary pockets of complexity under the right conditions. The emergence of intelligence may be less like a universal destiny and more like a rare crystallization event. Beautiful, intricate, but dependent on precise environmental factors. When we recognize this, the absence of obvious extraterrestrial civilizations becomes less mysterious. Instead of asking, "Why is the universe empty?" we might ask, "What extraordinary chain of events allowed us to exist at all?" And yet, we should avoid pessimism disguised as science. Physics does not say we are alone. It says the pathway to intelligence is narrow and contingent. New discoveries could overturn current assumptions. Perhaps life adapts to environments we once considered hostile. Methane lakes on Titan, subsurface oceans on icy moons, or exotic chemistries beyond our imagination. Maybe intelligence arises in forms we cannot yet recognize. Our search strategies are limited by our own biology and technology. The history of science teaches humility. Every time we thought we understood the universe completely, new evidence expanded our perspective. So where does this leave us? Intelligent life may be unlikely, not because the universe forbids it, but because it demands a rare convergence of physical conditions, a chemically enriched environment, a stable star, a protective planetary system, long-term climate regulation, improbable evolutionary transitions, and technological survival over cosmic timescales. Each step alone may be moderately probable, but when multiplied together, the overall likelihood shrinks dramatically. The silence of the cosmos may reflect this accumulation of filters rather than a single insurmountable barrier. And here is the most profound insight. The very physics that makes intelligent life rare also makes it precious. The same laws that govern stars and atoms have allowed matter to organize into beings capable of reflecting on the universe itself. When you look at the night sky, you are seeing the same nuclear processes that built the atoms in your brain. Intelligence may be the universe's way of becoming aware of its own structure, but only in scattered, fragile pockets. Whether we are alone or one of many rare civilizations, our existence carries a responsibility to preserve the delicate conditions that allowed intelligence to emerge and to continue exploring the cosmos with curiosity and humility. So the next time you hear someone say, "With so many stars, intelligent life must be everywhere," remember that physics invites a more nuanced view. The universe is generous with raw materials, but stingy with stable complexity. It takes billions of years, countless accidents, and an improbable chain of physical circumstances to produce a civilization capable of asking these questions. And perhaps the greatest lesson is not that intelligence is unlikely, but that it is astonishingly meaningful wherever it appears. In a universe governed by simple laws and relentless entropy, the emergence of curious minds is a quiet miracle, one that challenges us to keep searching, keep learning, and keep wondering whether somewhere across the vast silence another mind is asking the same question.